Hi, this is Professor Verkler, and this is Lecture 1-7 for ECE 1220 at the University of Utah. Today we will be learning about Kirchhoff's current law and Kirchhoff's voltage law, and how to use them to solve for unknown currents and voltages in circuits. So here's kind of a visual that's a good summary of each of the laws, and I will conceptually explain the photos here first, and then we'll actually go and do some math for each of the laws. So Kirchhoff's voltage law is kind of like the mountains in the left picture. When you go on a hike, you park your car somewhere and maybe you hike up a mountain 500 feet, then you go down 100 feet, then you go up another 300 feet along the ridge line to the next peak, and so on and so forth, as shown in that picture. But when you get back to your car, you always have to be at the same elevation. So the same is true with voltage. I might go through one device, maybe I gain 6 volts. Then I go through another device and I lose 3 volts, and so on and so forth around a loop in the circuit. But when I get back to where I started, the voltage better be the same relative voltages where I started. And then the second law is Kirchhoff's current law, and we can think of that like the rivers and streams in the picture on the right. So when two streams come together, all their water flows out together down the bigger river that they combine to make. So we don't like lose water into the earth or something, right? All the water that flowed in from the two different branches had to come out in the bigger river downstream. And so the same is true for current in circuits. When you have branches coming together in an intersection of wires in a circuit, all the current flowing in has to be equal to the current flowing out. Okay, so let's describe that formally now with math equations. So here's Kirchhoff's current law. And so the sum of the currents entering must equal the sum of the currents leaving. Our textbook shows this in a slightly different way. They consider the situation where all currents flowing into the circuit or into the intersection sum to 0. So that's what they wrote right here. So you could do all currents in or all currents out in that case. And that's mathematically equivalent to current in equals current out. So let's do an example here with this circuit on the left. Let's imagine that I1 is 5 amps, I2 is maybe 1 amp, and I3 is 2 amps. So then what must I4 be? Well, if you notice, these two arrows are going in, so I'll put them on the left side of the equation, 5 plus I4. And these two arrows are going out, so I will put them on the other side of the equation, 1 plus 2. So this tells me I4 is equal to 1 plus 2 minus 5, which is equal to -2. So what does a negative current mean? That just means it's current flowing in the other direction. So actually, I4 is equal to -2 amps, so I could also draw an arrow this way and call that +2 amps, if that's an easier way to think about it. Okay. So here's a poll to kind of test your understanding of the current law. I ask you to pause the video for a moment and like try to solve this yourself. And then in 5 seconds, I will solve this. Okay, so there are two places I could look on the circuit to solve this. I could look at this node down here where these 3 wires come together, or I could look at this branch up here where these 3 wires come together. Okay, so we know the current right here. And we know that because these two devices are in series. Therefore, the current here must equal the current here must equal the current here. So they are all 120 milliamps. Okay, so now at this node here, using Kirchhoff's current law, I have 50 milliamps going in, And I have I2 and 120 milliamps going out. Therefore, I2 must be equal to 50 minus 120 milliamps, which is equal to negative 70. Okay, now let's look at how to use Kirchhoff's voltage law. So again, we have a kind of generic formula here, which just says that if we sum up all the voltages in a loop, they must sum up to 0. So there are a lot of ways to go around a loop. I could go clockwise. I could go counterclockwise. I could start in the upper right. I could start in the lower left or the lower right. I could start in the middle up here. As long as I'm consistent and go in a full loop and get back to where I started, the math should work out. So I like to start personally in the lower left usually and go clockwise. So that's what I'll do here. Oops. And then the other decision you kind of have to make is, as you go through each device, are you going to look at the sign as you enter the device? Or are you going to look at the sign as you exit the device? I think there are advantages to each approach, and you can choose which one to use as long as you're consistent. So if you look at the sign as you leave the device, traveling through it, that kind of gives you a better idea of what's consuming power or producing power in your circuit. So it's better at kind of getting an energy sense for the circuit. The advantage to doing the sign of the device you're going into is, in the future, if you were to ever use mesh current, a method for solving for unknown voltages and currents in a circuit, it's a lot smoother if you use the sign of what you're traveling into in the component. So again, either method works. I'm going to do the method of the sign where you come out, but as long as you're self-consistent, it should work out. So let's do this. So first, I added 4 volts. Then I go through R1 here, and I come out the negatively labeled side, so I'll say minus V1. And then I come out the positive side here of V2. And then I come out the positive side of this 6-volt source. And then I come out the negative side of V3 there. And then I come out the positive side of V4. And that all must sum to 0. Let me move my head so you can see that. Okay. So let's practice. Again, I will give you 5 seconds now to pause the video as long as you need to try and solve this first. And please try and solve this first, because when you try to retrieve the knowledge you just learned from your memory, that's actually going to solidify the learning in your head and help you better remember it. Okay, so I will show going around the loop the other direction this time, just to show a different method, and I'm going to do the sign of the voltage as I go into the device. So we're looking at the sign of the voltage difference going into the device, and we're going counterclockwise this time. Again, as long as you're self-consistent, it'll always work out. So first, I have minus 3 volts. Then coming over here, I have minus V1. And coming over here, I have minus again, minus 1 volt. All that better sum to 0. So I'll move V1 to the other side of the equation. So I get negative 3 minus 1 equals V1. So V1 is equal to negative 4. So another way that people sometimes look at this is they kind of combine things in series. So I could, for example, say that these 2 devices in series are in parallel with the 1 volt source over here. And so negative 1 volt, because I'm measuring like here compared to there, better be equal to, these are both positive, V1 plus 3 volts, because things in series, their voltages add, we've learned previously. So that, again, should give the same answer, right? V1 is equal to -1 minus 3, which is -4 volts. So again, there are multiple ways to approach this. As long as we're self-consistent and make sure we go around the full loop, the math should work out. Okay, I have one more example to show you today. And this one is going to combine both our Kirchhoff's current law and voltage law. And we're going to have, and also Ohm's law. And we're going to have to use multiple problem solving steps. So I'm sitting here and looking at this circuit kind of wondering, like, what pieces of information do I know that will give me some other voltage or current in the circuit? So for example, right, if I'm at an intersection here, if I know 2 of the 3 currents, then I can get the third one. And kind of the things I like to look for first are like parallel, series, and nodes, which we learned about previously, and whether there's any information there contained in things being parallel or series. And then I'll start looking for like Ohm's law and KVL, the voltage law, and KCL, the current law. Kind of the order I'll be looking for things in. Okay, so first of all, I see these two are in parallel. So things in parallel share the same voltage. Therefore, the voltage across the 3 kilo ohm resistor must be 6 volts. Now, if we're going down this list, I can use Ohm's law, right? So this current right here, we'll label it I1. I1 is equal to V over R by Ohm's law, so 6 volts divided by 3 kilo ohms. So we do things piece by piece. 6 divided by 3 is 2. Volts divided by ohms gives amps. And then no prefix divided by a kilo prefix will give milli. Okay, so this is 2 milliamps. Okay, now I'm looking around, I'm like, well, I still only know one of the 3 currents here. But I do notice that in this loop right here, I know 2 of the voltages. So therefore, I can use KVL, the voltage law, to figure out what the voltage must be right here. So if I go around the loop starting here, looking at the sign coming out, I get plus 12 volts minus V2, and then going this way, minus 6 volts equals 0. So that means V2 is equal to 12 minus 6, which is equal to 6 volts. Okay, now I know the voltage and the resistance of the 2 kilo ohm resistor, so I can use Ohm's law to get this current right here. I2 is equal to V over R, so 6 volts divided by 2 kilo ohms. So again, 6 divided by 2 is 3. Volts divided by ohms is amps. And no prefix divided by kilo gives milli. So I have 3 milliamps here now flowing into this intersection. And I have 2 flowing out here. So that means that there must be 1 more flowing this way, because 3 milliamps went in and 2 milliamps plus I went out of the intersection. Now, I think you are ready to attempt the worksheet.